let's talk about forces that make things turn, because we've definitely talked about in the orthogonal components, we've talked about making things accelerate in one dimension, right? Circular motion is a particularly unique kind of case, because when we talk about acceleration, we talk about delta V over t. And if V final and V initial, let me write them as V minus V0. If V final and my starting velocity are in a line, it's really easy to add those things together. This is my initial velocity, 8 meters per second, and my final velocity was 2 meters per second in the other direction. I just declare a positive direction. Let's call that 8. That's my final. I would have -2 minus 8. The change is -10 because these guys are vectors. So in a straight line, it's really easy. Okay? If we can reduce everything to this, it's quite easy. The problem is when something turns, the direction of the force changes. And here's what it has to do with. If this is my V0 and this is my V final, it's turned, it's done this kind of thing. If we look at this, V minus V0, if we do it with vector addition, here's my V. Remember, subtracting, you're adding the negative of that. So you're adding, this is negative V0. And so what happens is actually the acceleration V is in the same direction as V minus V0, and that's in that direction. It really ends up being essentially perpendicular to the direction of travel. So if I'm going in this direction, I need to apply a force to cause an acceleration in that direction. Okay, and then that will make it turn a little bit. And then as it turns, I need to continue applying forces. And you'll see this is all towards the center of this arc. Okay, so even if I'm just turning like that, my force has to be towards the center all the time. It's real easy to see if you take something on a rope or on a string and you swing it around horizontally. If we look down on it, the rope will always be pointing towards the center, and the rope, that tension, is what is providing the force that makes this thing turn. So if we had no air resistance, you just went boom, and you just held it like that, it would continue going around like this, looking down on it. That tension would always be pointing towards the center from the object. So the free body diagram at that point looks like that. Free body diagram at that point looks like that. That force is always towards the center. And we call that force a centripetal force. And I should be really clear, centripetal force is not one force. It is the net force in the plane of turning, in the plane of the motion. And so when we say centripetal, it means center seeking. So anytime an object is moving at a constant speed, and I'm using speed instead of velocity because the velocity is constantly changing. So the magnitude of the velocity is constant in circular path. We say it experiences a net force towards the center. And we call that the centripetal force. Centripetal force is the net force. It's not one force. It's not a specific force like tension or friction or normal force. Those things can combine to provide a centripetal force, combine to make a net force towards the center. Okay? And a centripetal force, if we just go back to our sum of forces equals ma, that's the centripetal force if it's moving in a circular motion. It's that whole side of the equation. If we divide by mass, we get a very specific kind of acceleration. Again, it's not going from 2 meters per second in this direction to 4 meters per second in this direction. It's not strictly a change in velocity over time in one dimension. This is a multi-dimensional thing. And it turns out, and I can derive this separately for you, but it turns out that that acceleration is given by v squared, how fast it's going, divided by r. And there are a couple little changes that we've got to make to when we talk about v. Again, because that direction is constantly changing. So this is just how fast it's going. Okay, so what we end up with is sum of forces for something moving in a circle. Same equation, except now we're using v squared over r instead of a. I call this sometimes the AC, centripetal acceleration. So if I have an object moving in circular path at a constant speed, I can plug in that speed there, I can plug in the radius there, I can plug in the mass, and it has to be equal to the net force in that plane. Okay, let's do a problem. I've got a car going around a circle. Okay. And that car is traveling 10 meters per second. There we go. Car traveling in a circle. Okay, it doesn't have to be a full circle, by the way. It just has to have a circular arc. Okay, and it's going at v equals 10 meters per second, and I'm going to put that as magnitude. I also call this tangential speed or tangential velocity. Sometimes we call it linear velocity. In other words, not worrying about what direction it's going. We just care about how fast it's going. So you'll hear me say speed, tangential velocity, linear velocity. That's just how fast. Okay? So it's going 10 meters per second, and its velocity is 10 meters per second in that direction, then that direction, then that direction, then that direction. This is why we only talk about how fast. We don't talk about the individual vectors, the infinite number of vectors that are going into that. Okay? And I want to figure out how much force has to be exerted on that to keep it going 10 meters per second around a curve that has a radius of, let's say, 8 meters. So the way we do that is we write our Newton's second law equation. Sum of forces equals ma. But let me look at the free body diagram. I'm looking down on the car. Here's the car right there, right? And at that instant, it's traveling in that direction, tangential to the circle. Okay, so, excuse me. So what I need to do is I need to look at when I'm doing a free body diagram. Here's the car on the road. There are the tires. There's the street, right? And if I did a free body diagram here, I'd have mg. I'd have normal force. Let me draw it over here. mg, normal force, and friction. Okay? And friction actually has to be the force that's providing the force towards the center. If you think of it, if there was no friction, that car would just slide like that. Okay? So friction has to provide a net force towards the center to move it in a circle. So if we're looking this way at that car, we're looking at the headlights, right? The car's coming right at us. Look out. That thing, the friction would be in that direction. Okay, so you'd have normal force, this, and friction. So we don't care about this dimension so much. We can eventually care about that if we're trying to find the normal force, and if we have mu, and then we can use that to find the force of friction. But we really don't care about it for this specific problem. All I care about is looking down on it. In the plane of motion, there is one force on that car. There's no force pushing this way, this way, this way. The only things that are touching that car, you got field force, the only other thing touching that car is the normal force, which is coming out of the surface. We don't see that in this plane. That doesn't affect the circular motion. And friction. So we've got force of friction in there is the only force in the plane of circular motion. So when I'm doing this in the plane of circular motion, the net force is going to be the force of friction. It's going to be towards the center. The mass, I'm going to have to give you a mass, and v squared over r. So I start up here, sum of forces equals ma. I know that since it's turning in a circle in the plane of the circle, since it's got a circular motion, this is going to be a centripetal acceleration. I can substitute v squared over r, and then I can just solve, assuming I know the mass. I'm going to say the mass is 1,000 kilograms. Okay, you would have needed to know that. So the force of friction required to keep it moving in that circle would be 1,000 times v squared divided by r. Oh my goodness, I don't know how to do that in my head. That's 100,000 divided by 8, and that's going to be 12,500 newtons. That's a lot of newtons, okay? So it takes a lot of friction to turn a car that's going that fast around that radius. If we tried to turn it on an even sharper curve, this would be smaller, the 8 would be smaller, this would be much bigger. The smaller radius you're trying to turn on, the more friction you need to push in there, okay? If the mass was bigger, it would be a bigger number. If the velocity was bigger, it would be a bigger number for the force of friction required to turn it, okay? Now, if you think of this, that's how much force is required to turn it. If we looked at the normal force and this, we would actually kind of figure out what a critical mu would be. In other words, we could figure out how sticky those surfaces have to be for it to actually turn so it doesn't slide out, okay? That's one other aspect of circular motion. So what do you need to know? You need to know that the centripetal acceleration is v squared over r. We do our Newton's second law. Sum of forces equals ma. I'll come over so I can see you. Sum of forces equals ma. We substitute this in for the acceleration in the plane of the circle, and we figure out what forces are acting in the plane of the circle, and we can solve.